Okay, so let's continue with chapter 4. So we are still talking about work, energy and power, tapi sekarang ni kita nak combine semua. We talked about work, we talked about energy. We have not talked about power, but power ni macam a small section of this chapter only, and it's pretty easy. We're going to combine work and energy into problems and see how to deal with them. Okay. So let's do our recap as usual. So we know that we have learned about kinetic energy. Kalau korang dah bosan dah, I'm also bosan about this. Tapi kita kena ulang for those yang blur lagi So kinetic energy, we have kinetic energy. Kinetic energy is 1/2 mv squared and UG is mgh. Okay, so this is related to height, this is related to velocity. And US is your potential energy related to spring. And this is 1/2 kx squared. This is related to the compression or the stretching of the spring. Okay. Now, when we have a change in kinetic energy, we would have work done. When we have a change in UG, we would have work done. Ada orang nak tanya soalan ke? Okay, I think these are the ones yang baru masuk So then we have change in potential energy, elastic potential energy ataupun spring potential energy is the same thing. Elastic ataupun spring potential energy. To be more specific, we call it spring potential energy sebab other types of elastic material tak pakai equation yang sama. This is specifically for spring systems. So spring potential energy is it's going to be work done as well. Now, the interesting part about kinetic energy is that when the system only changes in terms of its velocity je yang berubah, you would have the work energy theorem. It's called the work energy theorem. And this only happens when velocity sahaja yang berubah, work energy theorem. Okay, for example, you have a box that is moving with u equals to 15. You move the box, it is moving by a distance called s. And then you have some force, right? Because we're doing work here. So we have some force that is pulling the box. It is moving, it is in motion and it traveled by distance s. And when it reaches the end point, there is some velocity involved. The velocity changes, there is acceleration involved. So here, the only thing that changes on this system, ataupun the only thing that changes on this box is the velocity. So you can say, oh, I have force and distance, that is work. So my work can be equal to the change in kinetic energy because that is the only thing that is changing here. The height does not change. You don't have a spring. The only thing that is changing is the velocity. So you can say, okay, I can use the work energy theorem to solve this. So F dot S, solve that first, and then this becomes 1/2 mv final squared minus 1/2 mv initial squared. You know what U is, you know what the mass is, you know what F and S is, you can solve for your V final. So this is how you use the work energy theorem. Whenever your system is not experiencing a change in height, it does not have a spring, it only changes in terms of its velocity. So this is when you use it. Okay, so moving on. Here we are assuming that our force here is a constant. Okay, it's not a variable force. I'm assuming that I'm pulling this box by 10 Newton. That's a constant force. I'm pulling this box by 15 Newton and 15 Newton does not change even though I reached my destination. So I'm assuming a constant force, therefore a constant acceleration. So this is very important. I don't think we can use the kinetic work energy theorem with a variable force. Tak boleh. So you only have to use it's a constant force lah for the work energy theorem. And then you have instances where your work done becomes positive. When your work becomes positive, you know that the speed is increasing. This is your V is greater than U. Your speed is increasing. Whenever you have a negative work, if you're using this work energy theorem, your U will be greater than V. So you would have a negative work. What else? Okay, so recapping the work energy theorem, it is the net work done. It is the net work. This is total ataupun net. The net work done on an object is equal to the change in its kinetic energy. Net, net work done. So if you have a lot of forces acting on this system, you need to find out what is the net, what is the total, what is acting in this motion punya direction, what is parallel to the motion ataupun displacement. And then you find out what is the net, and then you equate that to the change in kinetic energy, net. Very important word here, net. So this is your equation. Okay, so what else? New slide. Soalan boleh tanya, just interrupt me. Design. Home layout. No. This one. Design pula ni. Alright, so now kita cakap pasal conservative forces. So I told you we had two types of forces, conservative and also non-conservative. Okay, sorry tulisan buruk macam biasa. So non-conservative, we know that it is friction. Contoh, the types of forces that are non-conservative force is friction and also air resistance. Now, the funny thing about these two guys is that when we lose energy by friction, I cannot recover this energy back again. For example, I have an incline. Okay, of course, an incline. So I have a sled here. Okay, this is not me, this is Iqbal maybe. So Iqbal is on this sled on an incline. So Iqbal has some potential energy because he is at a height, right? He is at a height. So we can say, oh, Iqbal has UG of mgh, where the mass is the mass of Iqbal and also the sled. And G is gravitational acceleration, 9.81. And H is the height from the ground. This is very important. You need to define your height from the ground or the reference point given in your problem ataupun in your example. So the height is with respect to the ground. You can't say, macam kita ada incline kat sini, you can't say, oh, height daripada sini ke sini sahaja. No, you can't say that. You have to take a legit reference point. So the reference point yang everyone knows is the ground. And sometimes the problem will trick you and say, bukan trick lah, dia akan bagi soalan tu bagi susah sikit. Dia akan cakap, oh, the reference is not ground. The reference is above the water. Let's say ada water kat sini kan. Okay, so your reference is here. So they can do that to you. So it makes the problem a little bit confusing. But always you need to know what is your reference point. In this case, it is our ground. So this is our H. So Iqbal has some potential energy. So when Iqbal goes down the sled and he goes down the sled, so his UG becomes mgh, and now H is a 0, so this becomes 0. So the energy is now converted to become kinetic energy. At the top, Iqbal was not moving, so V was 0, so kinetic energy was 0. But this guy was not equal to 0, UG was not 0. So as he moves down the sled, he is losing mgh. He is losing, right? At this point, he is mgh over 2. At this point, his UG is mgh over 3, maybe. So his UG is slowly decreasing as he goes down the sled. So this energy, this energy is converted into kinetic. This energy yang hilang ni, kita tak tahu dia hilang di mana, tapi sebenarnya dia hilang pergi jadi kinetic energy. So as he moves down the sled, his speed becomes faster and faster sebab this energy is now going into kinetic energy. It is being transformed. So this is what happens when we are talking about conservative forces. the energy from UG, it is completely transformed into kinetic energy. So if I say, oh, Iqbal had UG of 100 joules, I can say at the bottom here, KE, the KE that Iqbal has is also 100 joules because I am assuming that we are not losing to friction or anything else. So it has complete transformation. EI equals to E final. What is EI? We have KE, we have UG, we have US, and this is also KE, UG, and US. The only thing that is different here is this guy is the initial state and this is the final state. So, oh, all right. So KE Iqbal is 0, right? He was not moving, and when he was at the top, he was not moving. His UG was 100 joules. We don't have any spring system here, so it's a 0. And then when he reaches this point, his H becomes 0. So MGH, when your H is 0, this guy becomes 0. So this becomes 0, and then you don't have this guy, it's a spring. So your 100 joules is completely transformed into kinetic energy, whatever that velocity is. So that is when you have conservative forces. However, what if you have non-conservative forces acting here? So you have Iqbal has some friction on his slide. It's not apa nama dia? It's not smooth. It is very rough. So he will lose some energy from heat, from sound. Maybe when dia turun incline tu dia macam tu kan. So that is some type of energy. So sound, vibration, heat, the system is going to lose that energy in that form, ataupun we just call it friction. And this energy is not going to be transformed into the KE. So dia hilang. It is gone. So when we write that equation, it becomes EI minus WNC equals to EF. And this is non-conservative force whereby it is lost from the system. It's not going to be converted to become E final. No, it's just lost into something else. So this is what it means when we have non-conservative force versus konservatif. Konservatif dia akan transform balik jadi benda lain. Non-konservatif hilang. Okay, you can't recover. You can't recover it. So this is my take on it lah. Last time I told you I would explain to you guys again. So I think this is the easiest way to explain it. Okay. What else? Pula. So any questions so far? Is everyone okay?
Doktor.
Yep. Oh, kejap saya tak dengar.
Nak tanya. Untuk yang sign of work tu kan, kalau dapat the value is positive or negative, so does that mean that if it's positive work, it means that the object is gaining energy?
I wouldn't say gaining lah. Dia macam mana? Cakap dia positive work, dia gaining energy. Yes, it is gaining energy, tapi dia kena dapat daripada somewhere else. Does that make sense? Macam mana cakap? So we know that our E initial has to be equal to E final, right? So when the system takes energy from, nanti dah jadi susah dah kejap Macam mana saya nak ceritain tu? Betul. Your statement is correct. When we have positive energy, when we have positive work, it means that our change in KE is positive, right? Or if we have positive work, our change in UG is positive, and etc. When we have positive work, our change in US is also increasing. But this energy that we get, the gain in the kinetic energy is taken from somewhere else. Let's say the gain from KE is gain from UG yang berkurang. So let's say this positive UG is gained by a KE yang berkurang. So it has to come somewhere. But you're right, positive work it means that this type of energy is gaining more. Betul. So that is why when we talk about the the work energy theorem, we say that a positive work is the KE is increasing, which means that your V is greater than U. So you become faster and faster. That has to come from somewhere. That energy to make that object faster and faster, it has to come from somewhere. But you're right, it is a positive work. But in this instance, selalunya kita akan ignore that energy tu datang dari mana. But when we're talking about EI and equals to E final, we are concerned where that energy goes to. So these are like different approaches lah. Ni macam ni nak tahu single type of energy je. Yang ni kita take into consideration all energy. Okay, so you're right, betul. Okay, so I want to talk about the spring potential energy. Sebab yang tu macam agak susah sikit bagi saya. Saya tak tahu korang rasa susah ke tak. But that's okay, kita akan belajar sampai kita faham. Semua benda susah kan? Okay, so spring potential energy, we have this equation, Fs equals to minus Kx, right? It is minus Kx. That is the elastic. Sekejap, saya rasa dia bunyi. Okay, sorry about that. It was my cat. My cat was like main loceng. Ingat kan siapa? Okay, so Fs equals to minus Kx. This is our spring system. Okay, so when you have extension ataupun stretching, you would have stretching Yeah. Nak cakap apa tadi Okay, I want to talk about the spring force dulu. So when I'm stretching the spring, I am extending this by 10 meter. Contohnya banyak ni. 1 meter, let's say. So this becomes Fs equals to minus K has to be a positive value because it is a spring constant. K is always positive, tak ada negative So let's say K is 10. So I can say minus 10. And then the extension is by 1 meter. So I say, okay, this is 1 meter, positive. I'm stretching it, becomes positive. So the Fs here is minus 10 Newton. It is a force. So the unit is Newton. So what does it mean when I have a negative 10 Newton? It means that whenever I'm stretching this spring, the spring said, okay, I don't want this to happen. I am going back to my original state. So what it does is that it applies the same amount of energy that I applied. I'm applying 10 Newton. This guy also applies 10 Newton. Dia akan berlaku pergelutan sebab the spring does not like being stretched or compressed. Dia nak go back to its original position. If you notice, if you're stretching it, you will feel that the spring is like pulling back at you. So this is what is going on. But whenever you are compressing it, so this becomes minus 1 meter. Remember, compressing is a minus, stretching is a positive. So the spring still does not like this. Dia tak nak orang stretch atau compress dia. So the Fs becomes minus 10. The 10 does not change. It's a property of the spring. Now this guy, this positive 1 meter, now it becomes minus 1 because you are compressing it. It is going to the left. I'm going to assume that's a negative. So this becomes positive 10 Newton. So what does that mean? It means that the force of this spring is going to act to the right because the positive 10 Newton. This was negative. When it was negative, it was to the left. When it was positive, it was to the right. So what I'm trying to say here is that you defined extension to the right as positive because if you did not define this as positive, you wouldn't know what the direction of your elastic force would be. let's say you say that extension is negative. Let's say you say the extension is negative, right? Okay, let me rephrase that. You have to define your direction of extension and compression so that you know which direction of force that the spring is doing. For example, if you say that your extension is negative to the right, you can say that. I'm going to say going to the right is negative. So I can see that. So if this equation becomes minus k is 10, extension is minus 1. So what does that mean? So positive ni negative, maksudnya sini positive kan? This means that I would get elastic force of 10 Newton. And I said to the right is negative, therefore to the left is positive. So I know that this guy is to the left by 10 Newton. So the direction that you defined earlier on tells you the direction of the elastic force. It doesn't matter if you're saying to the right is positive ataupun to the right is negative, asalkan kena define. Kalau tak define, you wouldn't know the direction later on. So defining your extension as positive or negative is important. I would recommend you guys to say extension as positive and compression as negative. Dia kena terbalik lah salah satu. Extension positive, compression negative. Compression positive, extension negative. Boleh, mana satu pun boleh. But you have to define it. Tak boleh sama Compression tak boleh sama dengan extension. It has to be opposite. That is the main point here. Compression and extension kena opposite direction. Because they are opposite direction anyway. And displacement is a vector. So you need to remember that. Okay, let me write that down as our note. Because I think some of you are confused about defining the compression and extension juga. Ada orang dah pernah tanya saya. So extension, X is positive. Compression, X is negative. Now, what does compression and extension mean? Okay, when you have a spring, you need to, and you're not doing anything to the spring, you need to define the equilibrium position. Okay, so this is new. We need to define the equilibrium position. I previously called this position as X equals to 0. I did not say the equilibrium position, but this is the same thing. The spring, when we're not doing anything on it, I'm not extending it, I'm not compressing it, we call this as the equilibrium position. It is at the equilibrium lah. Okay, so your X is 0. When you extend it, you are moving to the right. It becomes a positive X. When you are compressing it, this spring moves to the left. This point moves to the right, positive displacement. This point moves to the left, negative displacement. I always define my point that is moving at the end of the spring. Macam senang lah nak tengok. This point should also be your definition of equilibrium. This point. If you define kat tengah-tengah ni as your equilibrium, then kena ikut tengah-tengah ni lah. But that is going to be hard. Please use the end of the spring as your equilibrium position. Kenapa penting pakai equilibrium position ni? Nanti kita akan belajar yang kita boleh convert KE to UG, convert KE to US and US to KE from this situation. Okay, again, I'm going to repeat myself. Spring yang tak buat apa-apa, the hujung, the end of this spring is called the equilibrium position, or X equals to 0. When I'm stretching it, the spring extends, right? It extends, buruknya, it extends. So there is displacement of that end of the spring by positive X. When I am compressing, that hujung, that end of the spring is moving by minus X. Okay, so I hope everyone is alert on this one. It's very important because I will bring this same thing when we learn about transformation of energy of a spring. Okay, So apa lagi saya kena cerita kat sini? Okay, so let's do examples. Nanti kita akan use this for our spring punya example. Okay. Alright. Sekarang berapa? Wow, setengah jam saya cerita. Lamanya. Okay, find the amount of potential energy of an object if its mass is 5 kg. Kita dah buat ke belum kelas K19? Dah buat ke belum? Yang ni? I honestly belum Okay, so we go.
Belum.
Okay, so example 4.9, find the amount of potential energy of an object if its mass is 5 kg at position 150 centimeter from the ground. Now remember, I told you our H is with reference to the ground. So this becomes a positive H if it is 150 centimeter above the ground. So this becomes UG equals to MGH, 5 times 9.81, 1.5. So this is your answer. And then example 4.10, an object of mass 5 kilogram, okay, is moved from A to C. Dia bergerak daripada A ke C by a force of 40 Newton. So kita tahu kat sini ada force yang tarik dia ke atas dan dia bergerak sebanyak 5 cm. That is the displacement here. Find the work done by the force. That's easy. Work done is equal to the dot product of force times displacement. The force is parallel to the displacement. The force is parallel to the displacement, so kita boleh terus darab. Excuse me. If our force is not parallel, you need to resolve it to become parallel. Paling penting kat sini force needs to be parallel to x. Force needs to be parallel to x. If it is not parallel, resolve it. Force is a vector. You can manipulate it. So that 40 times 0.05, use SI unit, you get 2 Newton. Calculate the potential energy of the object. So when it travels by 5 centimeter, it is gaining height by 4. So how do we know this 4? Kita guna Pythagoras theorem ataupun if they give us angle, you can say sine of theta equals to opposite over hypotenuse. So opposite is the height and whatever the hypotenuse is. So you would get the height. If they give you only 5 and an angle, they ask you, hey, what's the potential energy? Find the height over here. The height must be the vertical displacement from the ground. Vertical displacement, tak boleh 5 cm ni, tak boleh. So that's another thing I need to include in here. Where was it? This is vertical displacement. Vertical saja ataupun y displacement vertical or y displacement. So tak boleh parallel to the motion ke apa ke, it has to be height, it has to be vertical displacement. Let's go back to the example. So MGH, so our vertical displacement when I travel from A to C, my vertical height was 0. When I traveled to C, my vertical height was 4 centimeter. Vertical, So this is the vertical displacement experienced by this box. Therefore, our MGH is 5 times 9.81 times 0.04. Penting vertical displacement. And when you're talking about work done by the force, it has to be parallel to the motion. So it can be slightly confusing, tapi kena ingat definition, insyaAllah okay lah. So UG is vertical displacement, nama pun height kan. Okay, next one. A spring is stretched from 12 centimeter to 14 centimeter. Stretched from, So in its equilibrium state, this guy is 12 centimeter. When it is being stretched, it is going to be extended by 2 centimeters. So this is your positive. Is this your x? This is your x. The stretching. Find the amount of energy stored in the spring. So we know that this equation is 1 over 2 kx squared. And your x will be 2 centimeter. Please change it to SI unit. Given that the spring constant is 150 Newton per meter. So 1 over 2, 150 times 0.02 squared. Okay, these are pretty easy, just using the equation. Okay, moving on. Last time we did this, but I think we got the free body diagram wrong. So I'm going to repeat this question again. Excuse me. Sekejap minum air sekejap. Okay, kalau soalan boleh interrupt me. It's okay if you don't understand, just tell me. I will try to repeat benda yang tak faham tu. It's okay if you don't understand. Saya pun bila kot waktu saya student dulu. Physics was not my strength. Okay, so a crate of mass 10 kilogram is pulled up a rough incline. Okay, so we know that it is pulled up a rough incline. So the mistake that I did last time was I did not notice it was being pulled up. I thought it was going down. So it actually is starting, it's being pulled up lah. Okay, so the mass is 10. Let's write that here. 10 kilogram. Initial speed U. I need to make this U smaller because that looks like a potential energy. U is 1.5 meter per second. The pulling force is 100 Newton parallel to the incline. So that's great. F is parallel. So kita tak payah resolve. F pull is, let me label this as FP. F pull is 100 Newton parallel to the incline. So that's great, which makes an angle of 20 degrees with the horizontal. Horizontal adalah x-axis. This is 20 degrees. The coefficient of kinetic friction. Kinetic friction means this box is moving. That is the coefficient of 0.4. And the crate is pulled by 5 meter. So it is moving by 5 meters. So the motion, how do I label this? Macam tu dia naik atas. So this is 5 meter. So how much work is done by the 100 Newton force? So this is going to be an easy question because our force is parallel to the displacement. Sama direction. First of all, it's parallel and then the sama direction. Therefore, dia jadi positive work. The positive work. So how much work done by the F pull? This is 100 times 5 meter. 100 Newton times 5 meter. So this becomes 500 Newton meter. Or you can write it like this. 100 cosine 0 because the angle of force with the displacement is 0. 100 cosine 0 times with 5. Kenapa tulisan saya macam ni? So this becomes 1. 100 times 5 is 500 Newton meter. So sama je. So I can use the angle if I want to, but I can just ignore it because I already know that these guys are parallel and in the same direction. So I shouldn't be bothered. Kalau nak bother juga, letaklah equation tu boleh. Letaklah dia punya angle tu cosine 0. Boleh juga kan? Okay, next. How much work is done by gravity? Okay, so I forgot something. I need to draw the free body diagram. Kita terus tackle soalan tadi. So let's draw the free body diagram before anything else. So this is our mg. And we have friction. Friction is this way because we are moving upwards. Friction always opposes motion. And then we have our reaction force, which is always perpendicular to the surface. So these are very important. And this is our center of mass. All our forces come from the center of mass. That's the definition of a free body diagram. Okay, so what else? I need to resolve mg. Mg over here is going to be 20 over here. This is mg cosine theta. And this is mg sine theta. So mg sine theta is acting in the same direction as our friction. Okay, not a problem. So how much work is done by gravity? So this is A, this is B. So I can choose 2 ways to do this. Remember the definition of work. It is force times dot product of force with displacement ataupun force that is parallel to displacement. Kenapa dengan tulisan saya hari ni? It's like even worse than usual. Force that is parallel to displacement. So here I have mg. It is parallel to height. It is parallel to height. Mg is parallel to height, but we are increasing in height, but mg is going down. So it's opposite direction. Another way that I can do it is 5 meter times with mg sine theta. So I can do that. Okay, let's try it. So work done by gravity, FGM. I'm going to call this force of gravity. So this can be mg sine theta, because this is the force that is parallel to x ataupun s. We call this s. This is the force that is parallel to s. Therefore, I put this into my equation, but the angle between this force and the displacement is 180. And then I times it with S. Okay, let me repeat myself here. I have a force called mg sine theta. This is from our gravitational force. I have a force mg sine theta that is parallel to my displacement. It is parallel, so it's cool. We can find out what is the work done. However, the angle between these two vectors is not zero, it's 180. mg sine theta is here, S is here. Angle berapa? 180 degrees. Whenever you have like two opposite direction vectors, the angle between them is 180. So 180, you know that it's going to give you -1. So this answer is a negative work. Is anyone confused by this statement? Is everyone okay with this statement?
Okay.
Okay. Okay.
It's 5. So let's calculate what this is. So 10 times 9.81 times with sine 20 times with -1 ataupun cosine 180 times 5. So I would get minus 167.76. Okay. So I wanted to show you something else. Okay. So I told you that work done is force that is parallel to displacement. We have another force. We have our gravitational force parallel to height. Can I use this value or not? If I find out what is height, can I use it? Will it give me the same answer? Okay, let's find out. I need to remove this. Okay. Let's see C. This is sorry, this is still B. So I have just now the question asked us how much work is done by gravity, force of gravity, and our approach was to we resolved our mg to become mg sine theta and mg cosine. Okay, the dua kat sini. And then we used the force of gravity that was parallel to the displacement, and then that was how we found out work. But when we are moving this box up the incline by 5 meters, we are actually gaining some height at the same time. So the height here is sine of 20 times with 5. Betul tak? Opposite over hypotenuse, yes. So sine 20 times 5 is going to give you a height of 1.71. Okay. Macam mana saya dapat ni? Sine 20 opposite over hypotenuse. Okay, opposite is the height, hypotenuse is 5. Kita punya incline ni, dia punya length dia 5. So I got 1.71 meter. So mg is this way and height is this way. I'm gaining height when I move up the incline. So kita ada macam ni dengan macam ni. In this case is mg and this is height. The angle between them is 180 degrees. Sama macam kita buat tadi, mg sin theta and s is the opposite direction. The angle between them is 180 degrees. So if I wanted to find out what is the work done by gravitational force, boleh je. Sebab they are parallel. So mg cosine 180 times with h. So I would get 10, that is the mass, 9.81, cosine 180 is minus 1, and height is 1.71. So the answer is times minus 1 times 1.71. Once jawapan dia minus 167.75 joules. The exact same answer. Sebab apa? Sebab basically this is the end point. The end point, the way to get to this end point is either you go by 5 meter ataupun you go by a height of 1.71. And the only thing that work cares about is the force that is parallel to the motion ataupun the displacement. Force only cares about the force that is parallel to the displacement. In this case, we can define our displacement in the y-axis, or we can define it here. Boleh dua-dua. But if it confuses you, just stick with this axis lah. This is the easiest one. But if the problem kasih height sahaja, contoh lah, dia cakap, hey, what's the work done by gravitational force? And they only give you height. So this is another way to do it. Okay, so I hope everyone understands why we can use height, but we cannot use mg sin theta with height. Sebab mg sin theta is not parallel to height, but mg is parallel to height. But if this confuses you, just stick to mg sin theta times s. Boleh juga, sama je jawapan dia. Just another approach. Okay, so that is B. Any questions about B? Tak ada, so everyone's okay.
Okay.
So what is the total work done on the crate? This is, what is the mechanical energy loss due to friction? So this is non-conservative work done. So C, I need space. So this is C, work done by non-conservative force. First of all, we need to find out what is our friction. Friction punya, friction punya coefficient was 0.4. 0.4 times with R. Saya punya screen macam ni. 0.4 times R. Okay, so R is, this guy is not flying. Therefore, net in the Fy is equal to 0. Therefore, R minus mg cosine theta. Therefore, R is equal to mg cosine theta. So we defined our R. R is 10 times 9.81 times cosine of 20. So this is 92.18. Newton. So this is your R. Plug that in times 0.4. Saya rasa betul lah ni. 36.87 Newton. So we're not done yet. This is not your non-conservative work done. This is only force. Selalunya orang letak friction as the work done. Salah, friction is not work done. Friction is force. Work done is force times displacement. So for you to find out what is the energy lost by friction, you have to multiply friction with displacement. So friction is this way, displacement is 5, the opposite way, angle between them is a cosine 180. So friction cosine 180 times with S. So that is 36.87 times with minus 1 times with 5. So this is your non-conservative work done, ataupun the work done by friction. So 36 times 5 times minus 1. 36.87, sorry. Hope everyone is focusing sebab selalunya orang complain kat saya yang chapter ni susah. That's why I'm doing these problems. Okay, so I hope you are focusing lah. Okay, so this is going to be minus 184.35. We're losing energy due to friction. How much mechanical energy is lost due to friction? Minus 184.35 joules. That is how much we are losing. What is the total work done on the crate? What is the total work done on the crate? Kenapa? Okay, kejap saya nak susun balik lah. Dia dah macam serabut. Sekejap This is A and B. So C dia rata-rata. Let's put that down here. Oh, jawapan kat sini. Nanti saya akan share tulisan-tulisan buruk ni. Macam nak share pun malu. Tak pun korang tulis lah sendiri. Saya dah tulis dekat dalam kelas kan. This guy is not moving. Okay, never mind. Let me just write that here. Minus 184.35 joules. Okay. Pun tak cantik juga. Tak apa. Saya accept diri saya seadanya. So that is C. This is A. This is B. This is also B. How do I make space? Buang yang ni senang. Let me make this smaller. Okay, let's put B over here. Okay, so let's figure out what is the total. What was the question? Net work done on the object rasanya. What is the total work done on the crate? W total or W net? Same thing. Okay, so it's asking what is W net. So D is asking for W net ataupun W total. What you can do is add all the work done by each force acting on this guy. So we had the first work done, which is 500. So that is force by. So we had this guy. Sorry guys. Okay, so this is the work done by the pulling force, and then the work done by gravitational force. What else? We had the work done by friction. Do we add the work done by reaction force? Do we not? Do we add it or do we not?
No.
No,
Why is that?
not parallel.
Not parallel.
Not parallel, correct. R is not parallel to our motion. So it does not have any contribution. So let's stick to this axis lah. Kita akan abaikan axis H tadi. H ni kalau ada situasi yang dikasih H sahaja. In this case, kita tak pakai H, kita pakai this 5 kan. So kita akan stick to one axis. Please, when you are using one axis, you stick to that. If you are using H, everything else pakai H. Kalau pakai S, semua pakai S. Ataupun this parallel axis. Stick to one axis. Why I showed you height, because I wanted to show you that the energy is still the same even though they are in different axes. So you can use whichever axis that you like, but stick to one. Okay, so we have work done by pulling force, by Fg, and then by friction. And are we missing anything? Mg, friction. Are we missing anything tadi kan? Okay, so this is work by pulling force. This is 500. And then work done by Fg, stick to one axis. We're using S as our axis. So this is, what was it? Minus 167. 0.75. Kat sini tadi. Over here, and then friction force, work done by friction is minus 184.35 joules. So the net work here is 500 times with minus 167.75 minus 184.35. So the answer is, yeah, kita lagi kira ke apa ni? 167.75 dengan 184.35. Okay, so 500 minus that. I would get 147.9 joules. Betul ke tak ni? Sekejap Mana jawapan dia bagi? Betul lah, okay. So this is the same. This is the same, work done by gravity. This is 147.9. This is 8, kurang lah. Some error because of decimal places, it's normal. Okay, and then the last question is, what is the speed of the crate after being pulled 5 meter? What is the speed of the crate after being pulled 5 meters? So we can use the work energy theorem, or we can use our linear kinematics, or we can use apa lagi? Work energy theorem, kinematics. Okay, so there's one thing that I mentioned to you before. When you have work done, total net work done, and the only change that you are experiencing is change in velocity, right? And I told you tak boleh ada change in US or change in MGH. That is actually true sebab saya tengok dalam textbook dia macam tu dia akan bagi flat area punya situation to use the work energy theorem. So saya tak tahu kenapa PBL ni dia kasih when you are increasing in height to use the work energy theorem. I need to double check on this one. Okay, sorry. Sebenarnya jawapan dia macam ni. Jawapan dia macam ni Jawapan dia macam ni. Dia pakai work energy theorem. So the net work kita dah cari 147.8 sama. But they are equating it to change in KE. But from my reading, your change in KE kena on a flat surface, meaning to say that there is no gravitational potential energy yang berubah, there is no elastic potential energy yang berubah. So I need to check back on this guy. Okay, so for now, please use what I told you because I'm using the textbook and this is reference yang mungkin saya tak tahu reference daripada mana. Okay, so please use what I told you in the recap earlier. Kita akan discuss balik pasal work energy theorem if we can use it for an object moving up an incline or not. Okay? Next. Okay, faham ke apa yang saya cakap tadi? I think I was a little bit fast. Faham ke apa isunya? Faham kan? Okay. Okay, isunya is I told you when we use work energy theorem, the only change that I'm expecting when we use that theorem is kita punya velocity sahaja yang berubah. We're not going to change in height, we're not going to change in elastic potential energy ke apa ke, tak ada. Kita punya contribution hanya pada KE. So when there is other energy involved such as UG, I'm not sure if we can use that or not. So let me double check on that because example dalam textbook dia tak pakai untuk incline. So let me double check. Alright, so moving on, kita akan go to power. Nanti kita akan take a break after this example. How much power is delivered to a turbine below a dam? So this is our turbine. I don't know how a turbine looks like actually. Walaupun saya engineer. Let's just say it looks like this. So this is our turbine and ada power, ada a dam that is releasing water into this turbine. So how much power is delivered to a turbine below a dam? So this is our dam and it is flowing, water is flowing out of the dam into this turbine, into something, I don't know. What does it look like? Let's Google it. Saya rasa saya kena tahu juga, nanti saya nak cerita susah. So am I still screen sharing? Stop share. So let's take a look on how a turbine looks like. Okay, water. Ish, susah pula nak buat sini. Okay, kejap. Give me a minute. Okay, so water powering, hello. Water powering a turbine. Okay, so it looks like this. Okay, this diagram looks promising. Let's see. Serupa dia macam ni Gravitational vortex, water turbine. Don't know, jap. Okay, this one. Let's go for this one. Hydroelectric power, how it works. Why am I interested? I'm not interested sangat pun. Tapi saya nak tahulah juga sebab saya nak kena cerita. Okay, so this is the dam. Where's the dam? Is it okay? This is the reservoir. Goes into here. This is the turbine, and then it goes out. So when we talk about the turbine, this is our turbine. We are releasing water from here, and here to here has some height. Let's screenshot this and put it into our slide. Buruknya gambar ni tapi tak apalah. Dia macam poor resolution. Kalau saya increase pun tak boleh juga. Mari tak gambar lain sesuai. Gambar ni pun tak cantik. Okay, tak apalah. Asal yang kita faham sudahlah. Okay, stop sharing. Share. So if this interests you, that's good. Sebab this is one of the sustainable energy ataupun green energy. Why is it green energy? Because you always have water. You always have water and it does not pollute the earth, does not emit anything. So electricity that we get from hydro waste ataupun from water is very, very good actually. So bila diorang nak buat dam, however, when we create a dam ataupun when we build a dam, we are actually destroying forest. So ada macam konflik lah kat situ. We want sustainable energy, but at the same time we are destroying forests. So the way that we can do this ethically lah. The way that we can build dams ethically gets our sustainable energy, but at the same time not destroy forests is by good planning of cities, good planning of towns. Macam kita boleh declare, okay, this much of forest, don't do anything to it. This much of forest, we just build the dam, and this dam should be able to cater for the entire penduduk of that city lah, of that particular city. So kalau ada krisis, they should have oversee lah. Diorang patut boleh predict lah, okay, kalau banyak sangat hujan apa jadi, kalau ada kemarau apa jadi. Diorang dah kena plan dam tu so that they don't have to create another dam. They have to do the dam, the first one that they build, they have to do it properly so that it can sustain the entire city and akan boleh cope with whatever natural disaster that happen lah. So we want that sustainable energy, but we have to do it at the sake of forest. So kita kena ada proper planning. So that is why when orang cakap, oh, let's build this dam, or akan ada protest, there will be protests because you are actually destroying valuable forests. And we need forests because kalau tak ada nanti jadi panas, and then kita akan ada banjir when we don't have enough trees supporting kita punya bukit. When there's a lot of rain, then akan ada landslide. So there's a lot of things involved when you build something. That is why protests are going on when they are destroying forests. So that if that interests you, that is very good because benda tu sangat penting for our future. Saya pun sangat takut kalau diorang nak destroy all the forests, what will happen to my kids? Will they have a nice place to jog? Will they have a nice park to go to? Ataupun adakah semuanya akan jadi cement? So I don't like that. So that is very interesting lah. And hydroelectricity, you need to have proper planning to build stuff like that for the dam. All right, so enough chit chat about that. So let's continue with this guy. Where's my screenshot? So personally, I'm not interested in hydroelectricity because, of course, that's not my specialty. But I'm very interested into green energy. but not specifically that type of architecture. But if you like that kind of architecture, you're very interested on how we can create more energy from water, then go for it. I really recommend going for it. Sebab green energy is always relevant. Green energy will always be relevant. It will not be out of date. Macam fossil fuel, there will be a day where we won't have any fossil fuel left. But sustainable energy, there will always be sustainable energy. We are always going for green energy, solar power, water, wind, stuff like that. Okay, so increase pada insert. All right. Let's go for this guy. Okay, so this is what it's trying to tell us. Draw. Okay, so it says how much power is delivered to a turbine below a dam of height 50. Height. So this is 50 meter macam tu. So dia daripada sini, dia turun sampai ke turbine. So ada potential energy yang associated when we go to this turbine. When we go down, we are losing potential energy. Where does it go? It goes to the turbine. So how much energy, how much power is delivered to 50 meter that delivers 1 meter cube of water in 1 minute? So the time is 1 minute. And our volume. So korang fikir, benda pula volume ni, kita cakap pasal work. Yes. Now they have given us the density of water. So with volume times with the density, you get your mass. So that is how you get your mgh. So mass is density of water macam tu ke rupa dia? Bukan density rho ke? Kan density rho kan? Rho times volume. So that is 1000 times with 1. So that is 1000 kilogram. Yang ni 1000 tadi tu kilogram per meter cube. 1 was meter cube, darab dengan meter cube, cancel out with meter cube, I'm left with kilogram. So mass is density times volume. So I have 1000 kilogram. So when my water starts from here and then it goes down to the turbine over here, I start with UG. So UG is mgh 1000 times 9.81 times with the height from, this is our reference point line. Our reference point is the turbine. Our reference point is the turbine. Sebab kat sini kita tak tahu ground kita kat mana, so kita akan anggap the distance to the turbine is our reference. So 50 meter. So that is 1000 times 9.81. Okay. Berapa? 1000 times 50. 490,500. Okay, so this is the energy that it started with. When it goes down, dia akan bagi energy dia kepada turbine. So how much power is delivered to a turbine below a dam of 50 meter? So the equation for power is work over time. The equation for power is work over time ataupun energy over time. Okay, so this is the equation. I think everyone should know this. Kalau tak tahu, saya bagi tahu sekarang. Power is work over time ataupun energy, the change in energy over time. In this case, our work ataupun energy is 490,500. When it moves down here, the UG obviously goes to the turbine. The UG is, when we go down here, mgh akan jadi kosong. Kat sini dia jadi mg 50. So energy tu has to go somewhere. So the energy goes to the turbine. So we can say that there is some change in energy going on, but we don't know exactly how the equation looks like. So kita akan cakap, okay, it's just work done equals to 490,500 joules because it is being transformed. And then we divide it by 60 seconds. So P is equal to 490,500 divided by 60 seconds. Jawapan dia adalah 8175 watt. Okay, so this is how you do it. We start with energy. and then we divide it by, ataupun work done divide by time. Itu saja. Equation power senang, paling senang lah setakat ni. Okay, let's take our break. Sama jawapan dia. Kat sini dia buat 8.175. Kita punya jawapan 8175 watt. Sama je. This is kilo. Okay, so let's take our 7-minute break. Let's come back at 11:25 a.m. Okay, we have still a lot more of examples to go through. Get your water or snacks, whatever that keeps you awake. Kalau soalan boleh tanya.
Doktor,
Yep.
yang PBL 4.4 tadi tu, yang soalan B tu kan dia ada cos 180 kan? Itu sebab dia terbalik ke apa?
Sebab dia terbalik.
That
Angle,
means, okay.
so angle between mg sin theta and x, satu vektor ke sini, satu vektor ke sini, angle between them is 180. Kalau diorang sama direction, then angle between them is kosong kan? Kalau terbalik 180.
Oh, kalau dia terbalik kena tulis cos 180 lah.
You don't have to put in the cosine 180. Kalau nak cakap dia negatif terus pun tak apa. Remember work done that is in the same direction positive, work done that is opposite direction is negative. So you don't have to write the cosine 180 if you understand the first part and just letak negatif tu sendiri. Faham tak?
Alright, faham. Thank you.
You're welcome. Pukul berapa? 11:22. time? Oh, it's time already. Okay. So sebenarnya kan ramai juga yang tanya saya yang cosine 180 ni. So let me clarify that. Bukan dalam kelas je yang tanya, dia tanya dekat WhatsApp pun ada. So I think that's a little bit confusing for you guys, I think. So remember, kita punya definition for work done is the dot product of F and S, right? And I told you, when we expand the dot product, we have F cosine theta S. What does the theta represent? The theta is the angle between the force and the two vectors lah, angle between the two vectors. Okay, so the first condition for work done is it needs to be parallel. If it's not parallel, you find the component to be parallel, and then bila dah dapat component of parallel tu, find out whether it is the same direction or opposite direction. Okay, contohnya, or opposite direction. If they are same direction, F dengan S sama macam ni, angle between them is cosine 0. If they are opposite direction, F macam ni, S macam ni, ataupun F macam ni, S macam ni, the angle between them is 180. Sebab memang angle diorang terbalik lah, 180 Seorang kat kanan, seorang kat kiri, angle between the two vectors is 180. If F dengan S, dia sebenarnya dia ke atas line yang sama. So angle dia adalah kosong. Dia orang tak separated sebenarnya. Dia orang atas line yang sama. If I were to redraw this is F and this is S. Direction sama. They are on the same axis. Angle between them. Ada tak angle? Tak ada angle kan, kosong. So cosine 0. Cosine 0 is equal to 1. Cosine of 180 equals to minus 1. If you don't want to use the angle approach, you would just want to say, okay, if F and S are the same direction, work done is a positive. If F and S are opposite direction, it's a negative. You can do that as well. You don't have to put in the cosine 180, cosine 0. I'm just showing it to you guys if in case you want to use this equation. If you don't, just use F parallel S, where sama direction, same direction, positive, work. Opposite, negative, work. Boleh juga. Okay. S dengan F terbalik 180 degrees. S dengan F sama direction 0 degrees. What if F is this way and S is this way? Angle 180 degrees. Tak kisah arah macam mana pun, asalkan terbalik. Asalkan dia terbalik 180 degrees. Macam ni boleh. F macam ni, S macam ni, 180 degrees. Half a circle, half a circle is 180 degrees. Full circle is 360. This is the half circle. They are opposite and the angle between them is a half circle. Apa lagi? Is that okay? Does everyone understand why is a cosine 180, or we can just not use cosine 180, we can just say it's negative? Faham ke?
Faham.
Any other questions about this one in particular? No more questions? So everyone's okay, yeah? All right, let's continue with our next example. Where is it here? Okay. Okay, so a block of weight, a block of weight 120 Newton is moving downwards along a plane. So dia ke bawah. So it's moving downwards. Why is my incline like that? So this is, why is it like that? So hard. Okay, so a block of weight 120 Newton is moving downwards along a plane inclined at an angle of 30 degrees with a horizontal at a constant speed of 10 meters per second in 3 seconds. So constant speed, constant speed. What does constant speed mean? What do we know about constant speed? What do we know about constant speed?
V sama dengan U.
V sama dengan U, okay. What else? Betul, V sama dengan U.
Acceleration 0.
Acceleration is equal to 0, correct. So when we have acceleration equals to 0, what do we have? What does it mean? Is it in equilibrium or non-equilibrium?
Equilibrium.
Yeah.
It's in equilibrium, but in dynamic equilibrium. Dia bergerak, but at a constant speed. There's no acceleration, there's no force, because it is in equilibrium, but it can still move. So this is called dynamic equilibrium. You just have to know that it is equilibrium lah. So when we have equilibrium, we know that our fx must be equal to 0. So this is our imaginary axis. The best axis is to use the one parallel to your motion. This is from chapter 3. This is your y. So you have a weight of mg, which is 120. Let's just label this as 120 terus. And this would be 120 cosine theta. And this would be 120 sine theta. And since this is moving down the incline, motion is this way, this is x, you would have friction on the opposite side. What else am I missing? I'm missing reaction force, R. Okay, so a block of weight moving downwards and then constant speed, u v equals to u, so a equals to 0. Therefore, we know that it is in equilibrium. So the net in the fx is equal to 0 is asking about friction, but we don't know what friction is. We know what friction is if we use this equation lah, but we don't know what the work done is. So let's try to figure this out. So net in the fx is equal to 0. What do I know here? I have 120 sine 30 in this axis minus friction, and this should be equal to 0. And 120, so friction is equal to 120 sine 30, or
60.
60 Newton. So your friction is 60 Newton, but I still don't know what is my work done. So work done punya equation is friction times with the displacement. But in this case, we know that friction is in the opposite direction with x. Friction is in opposite direction with x. So cosine 180 ataupun minus 1 times with x. Now I need to know what is x. How do I find out x? It says constant speed of 10 meter per second in 3 seconds. How can I find s using this information? Ataupun x, s lah, s. Let's label this as s. How can I find out what is my s? Sama je s dengan x ni, jangan confuse pula. Okay, so no one wants to try? What about linear kinematics? Can we use linear kinematics?
V sama dengan U plus 80.
V equals to u plus 80, and Rai said speed times with time. Okay, let's try it. V equals to u plus 80. V equals to u plus 80. So V is the same, U is the same. V minus U is 0. A is 0. So this doesn't solve our this doesn't solve our question. We want to know what is S. Teka lagi, apa lagi equation? Kita nak tahu S kita apa.
V square equals to U square plus 2AS.
Plus 2AS. Okay, let's see. V squared U squared plus 2AS. A is 0. V equals to U. Doesn't really solve S. What else? So Rai said V equals to U times T. S equals to U times T. S equals to, sorry, S equals to U times T. This is what Rai said. So S equals to U plus T comes from the equation S equals to UT plus 1/2 AT squared. This guy is 0. U is equal to V. So we are good to go. 10 times 3. So we get 30 meter. So this is how you find out the displacement. Do you need to use the entire equation? No, you can just use this guy if you already understand how to use it. So S equals to U times T. 10 meter per second times with 3. So you get 10 meter per second times with 3 seconds. You are left with meter. Pakai macam ni pun boleh terus pakai. You don't have to use the linear kinematic pun sebenarnya. So 30 meter. So now we can put 60 cosine 180 times with 30 meter. So this is 1,800 but a minus 1,300. Minus 1,800, sorry. Minus 1,800 joules. So the work done per second to overcome friction is, what did you have per second? Per second. Joules is meter per meter. Tapi tanya work done. Let's see. Oh, betul lah, dia suruh cari power. Okay, so we got the 1,800, the work done per second. This is definition of power. Tu yang saya macam, kenapa dia tanya pasal power? Betul, memang dia tanya pasal power pun. So power is work done over time. So 1,800 over 3. So you would get 600 watt. So this is the final answer. So the work done per second is power. Okay. So it is 600 watt. Unit untuk power is watt. Watt. Okay. Moving on. Yang ni kita dah buat. Ini pun dah buat. Kenapa kita patah balik? Baliknya. Okay. Next one is wax your skis. Okay, this is from the textbook. Kalau korang tak pernah buka textbook, saya bukakan untuk korang. So this is example 5.4. I believe this is from page 132, 131 lah macam tu. 1,131 page 131. So nanti boleh tengok dekat buka website, kat situ tulis ebook kan, tekan ebook kat situ. So this is example 5.4. I believe this is a very important example that we need to go through. So a 60 kilogram skier is at the top of the slope. So sekarang dia dekat point A. The skier is at point A. At initial point A, she is 10 meter vertically above point B. So this is point B, but the question is saying 10 meter vertically above. So we are talking about height here. Okay, so setting the zero level for gravitational potential energy at B, setting the zero level, so this is our reference point, where H becomes 0, and this is where H is 10. Okay. Find the gravitational potential energy of the system when the skier is at A. So dia nak suruh cari UG equals to mgh at point A. Okay. And then at B. So dia suruh cari UG mgh at point B. So this is the question. Find the gravitational potential energy of the system when the skier is at A and then at B. Finally, find the change in potential energy of the skier Earth system as the skier goes from point A to point B. So dia suruh cari change in UG. So this is our UG initial, this is our UG final, and it's asking us to find the change in UG, which is UG final minus UG initial. And then B, repeat this problem with zero level at point A. Repeat again with zero level 2 meter higher than point B. Okay, let's do the first one first lah. So strategy kat sini, follow the definition and be careful with signs. A is the initial point with the gravitational potential energy PEI, and B is the final point. This is what we said just now. With the gravitational potential energy PE final. The location chosen for y equals to 0 is also the 0 point for potential energy because PE is mgy. So whatever point that we use as our reference, in this case, our ground, the potential energy will be 0 because mgh, when h is 0, therefore our UG is also 0. So number A, ini senang je lah, saya nak tunjuk konsep je dulu. UGI, M is 69.81, H is 10. So we started with 60 times 9.81 times with 10. So it is 5886 joules. For our UG final, it is at this point B, kita punya height kosong. So this is 69.81, 0. And this would be 0. And the change in UG would be final minus initial. So I would get minus 5886 joules. So we solved for A. Kejap. Repeat this problem. Okay, kita tengok B. Kenapa tulisan kecil sangat? Repeat this problem with 0 level at point A. So sekarang dia cakap height is 0 kat sini. Sebab kenapa? Suka hati dia lah kan. Dia nak kata ni reference point kan. Boleh. Okay, so this is our job to make sure we understand what is going on. So H is equal to 0 kat sini. The skier goes from, repeat this problem with 0 level at point A. Therefore, if we are going down, we are going by minus 10, right? So this becomes minus 10. So boleh ke kita buat macam ni? Boleh We can pick whichever reference point that we want actually. The problem can pick whatever reference point that we want, that they want. Tugas kita adalah untuk menyenangkan hidup kita. So kita selalu pilih ground. Tapi problem tak nak senangkan hidup kita. So dia suka hati dia lah nak pilih mana kan. So kita kena tahu macam mana nak buat if they choose a different reference point. So in this case, the reference point is at A. H is 0 there. And then this guy, H is minus 10. So what happens to our equation? So let's do it. So B equals to UGI equals to MGH. H is a 0. So UGI is 0. Looks a little bit confusing. Let's just go with it. UG final is MGH. And this is 60 minus 9.81 minus 10. This would give me minus 5886 joules. Final step is finding the change in UG. This is UG final minus UG initial. So the answer is minus 5886 minus with a 0. So you just get 5. You just get the 5886 lah. So this is your final answer. Sama je. So the point being here is you can have whatever reference point and you will still get the same answer because when we talk about change in potential energy, we only care about the change lah. We just want to know what is the change. So you can label this as your reference point. You can label this as your reference point. It will still give you the same answer. So this is something that we need to be aware of lah. Okay, so the change in potential energy is about relative energy. So the energy at point A is relatively greater than the UG at point B because point B ni tadi kita tengok point B adalah minus 5886. UGI is 0. So point A has 5886 greater energy than UG final. Faham tak? Sebab dia kosong. So energy dia lagi besar daripada UG final sebanyak 5886. Energy dia adalah 5886 lagi banyak daripada UG final. This is point A. Point B, dia punya energy adalah kurang daripada 5886 daripada point A. So sebenarnya kita cari relative energy. Benda ni tak absolute lah maksudnya. Okay, saya go kat sini pula. So UG initial adalah 5886 joule. Tadi when was H equals to 10 and this is H equals to 0. So at H equals to 0, the energy at this point is kurang daripada point A sebanyak 5886. Faham tak saya cakap ni? Dia relative energy So this point A is greater, faham So this point A is greater, ya Allah, nak tak tulis ni. This point A is greater than point B sebanyak 5886. Dia lagi banyak sebanyak 5886. Tak kisah cara nak kira tu macam mana. Yang kita tahu relative energy adalah A mesti lagi besar daripada B sebanyak 5886. Tak kisah kita nak define this point as H equals to 0 ataupun H equals to 10. Relative energy sahaja yang kita nak tahu. Okay, so gravitational potential energy is actually a relative energy. And when we talk about UG equals to mgh, we are always assuming we are referring to ground level because that is our reference point. Sebenarnya dia relative energy. Okay. Kalau kita cakap pasal, okay, tak apalah. I'm going to stop at there. I hope everyone understands this part. Gravitational potential energy is a relative energy. When we talk about UG equals to mgh, we are actually talking about reference point kita as ground, which is 0. Sebab tu kita boleh pakai UG equals to mgh. Tak perlu pakai mgh final minus mgh initial. So, kita tahu initial kita kosong. So UG is just that. But when we don't have a conventional reference point, ataupun we don't have ground as our level 0, then we have to do the math. Kita kena tolak diorang. Final minus initial. Okay. So this is what the answer is. Minus 588. Samalah. Sama dengan jawapan kita tadi. Repeat the problem if y equals to 0 is 2 meters above B. Does that mean? 2 meters above B. So dia nak cakap kat sini. Let's duplicate this gambar. And then remove the rest. I hope I'm not confusing anyone. If you are confused, please discuss with me. Sebab when you don't know, when you have lack of information, I think that will make you confused even more. So I'm just giving you everything lah supaya it makes sense. Okay, so dia cakap what? Tadi kita cakap mula-mula H kat sini 10. And then kat sini H kosong kan? Tu mula-mula. Then dia cakap okay tak nak macam ni. Dia nak H kat atas ni kosong. Kalau H kat atas ni kosong, then H kat bawah ni minus 10. Okay, lepas tu dia cakap okay dah dapat jawapan kan? Okay, dia nak bagi susah lagi. Dia cakap tak nak macam tu pula. Dia nak kat sini. Dia nak dekat sini 2 meter above point B. 2 meter above point B is H equals to 0. Dia nak kat sini pula. So maksudnya kat sini, point kat sini adalah minus 2. And at this point, H is going to be 8. Perbezaan antara point final dengan point initial masih 10. This is the important point here. Masih 10 So atas ni 8. Kat tengah-tengah ni kosong, bawah ni 2. Apa yang akan berlaku? So let's find out. Jawapan dia patut sama because gravitational potential energy is a relative energy. So dia tak akan kisah pun apa H punya value pun. Asalkan relatif dia sama. So kat sini UGI adalah 8, UG final adalah minus 2. 8. Okay, this is initial. Atas ni H equals 8. Final adalah minus 2. So kalau 8 kat sini jadi sorry. Okay, let's see. 60 times 9.81 times 8. So dapat 4708.8. 60 times 9.81 times minus 2. Dapat minus 11772. UG final minus UG initial. So 11772 minus 4708.8. You would get minus 5886 joules. So here they proven to you no matter what the H is, asalkan initial dengan final point dia perbezaan dia sama. initial dengan final perbezaan dia sama 10. Setiap masa 10. Maka relative energy UG juga adalah sama. Okay. Jawapan dia tetap sama. Okay. So semua sama. Yeay. Itu saja. Okay, next. Platform diver. Ada soalan tak setakat ni? Lagi 10 minit je. Tak sempat buat spring. Tak apalah, nanti kita buat spring next class. So platform diver. Kejap. Oops. Tekan benda lain. Okay, so platform diver, a problem pula. A diver of mass m drops from a board 10 meter above the water's surface. So adalah kat sini 10 height from the water surface. Kat sini adalah h equals to 0. To reference point. Neglect air resistance. Yay. Use conservation of mechanical energy to find his speed 5 meter above the water's surface. It doesn't want to know what is the speed at h equals to 0. It wants to know what is the speed here. Okay. Use the conservation of mechanical energy and then find his speed as he hits the water. Kat sini pun nak tahu juga. Dia nak tahu V dekat sini apa. Nak tahu V dekat sini apa. So kita akan cuba buat V kat sini apa dulu. Okay, so conservation of energy. What is the equation? So it is EI equals to E final. We are neglecting air resistance. Therefore, we don't have any non-conservative work done. So that's great. So EI is KE initial plus UG initial. Kita tak ada spring kat sini, so we don't have to include that. So KE final plus UG final. No non-conservative force. Air resistance is neglected. Okay. So this is our starting point. Now we try to fill in our equation. Kalau ada soalan ataupun confusion, interrupt me, please interrupt me immediately. Your question will help your other friends as well. So don't be shy. So KE, kita start dari sini kosong. Sebab kita baru nak terjun kan, so kosong. Kita start dari 0. And then our PEI is MGY initial. So this is MGH initial ataupun in this case it is 10. And then our KE final, we say that this is our final point for now because we want to know what is our V here. We make this as our final point dulu. So this is at height equals to 5, right? So KE final is 1/2 MV final squared. Our VI is 0 plus with UG final. UG final is MGH equals to 5. So this is MGH final where H is equal to 5. Yang ni adalah H equals to 10. This is our initial. This is our final. So kita plug in our values now. So M is, what is M? Okay, so M kita boleh cancel out sebab semua orang ada M. Factor out M, cancel it out. So now we're left with GHI 1/2 VF squared and GH final. So this is 9.81. HI is 10. 1/2 V final squared plus with 9.81 times with H final. H final kita ada 5. This is, this is not squared. This is just 5. So this guy minus with this guy times with 2 square root. Berapa dapat V final? V final is 9.81 times with 10 minus, 10 minus 5. You get 49.05 times with 2 square root that. So you get 9.9. I hope I'm betul Sekejap. Okay, 9.9 betul. Thank you for the extra help. So I got 9.9. If I say that this is my final point, so the velocity of this guy at height of 5 meter is 9.9. He started with KE equals to 0. He started with V equals to 0. At this point, he became 9.9. So sekarang kita nak tahu what is the velocity at this point. Okay, kita tinggal 5 minit. Let's try to wrap this up. Okay, let's make this small. Oh, saya lupa ni lab. So tak adalah macam terkejar-kejar sangat. Okay, so EI equals to E final. But don't worry, I will end at 2 hours. Don't worry, saya pun tak lari nak cakap lama-lama. Okay, so KEI plus UGI, sama juga step yang sama. But now this is our Y final. This is now our Y final. Tadi punya cerita tadi lah kan. Sekarang cerita baru. This is Y final. So kita ada KE final plus UG final. KE is 0 at the initial point. UG adalah 0 at the final point. So sekarang hidup kita dah mudah sikit. Bersusah-susah dulu, bersenang kemudian. Kat sekarang ni kita punya H is equal to 0 at this point. This is our reference point. MGH is equal to 0 sebab H kosong. So now we have mg times with 10, 1 over 2, mv final squared. So senang je lah kat sini, m cancel out, 9.81 times 10 times with 2, and you get square root of that. So your v final is actually 14 meter per second. Kenapa? Sebab our entire UGI is converted into KE, completely converted into KE. Dah tak ada dah yang tertinggal jadi MGH. Tadi kita punya velocity 9.9 je sebab kita punya initial energy ni kena berkongsi. Berkongsi antara dua ni. So ada MGH punya energy, ada KE punya energy. So KE tak sampai full potential dia. When this guy reaches the ground where the potential energy is 0, all of that energy from the initial UG went into kinetic energy. So sekarang dia punya velocity lagi besar. Complete transformation from UG into KE. This guy, transformation of UG into KE plus UG. So dia kena share. So KE kurang. Ni KE tinggi. Okay, so I hope everyone understands those two examples. Boleh guna ebook untuk baca example lain juga. We will do examples on spring lepas ni. Oh, this is another one on incline. And then ada tak spring? Spring ada, yes. Saya design saya punya problem ni ada spring. Okay, so that is it. Next class kita akan belajar pasal little bit more on MGH, and then kita akan sambung with spring punya example. Any other questions before we end class? Everyone's okay? Dah faham dah ke what is MGH and KE about? Yeah. So I hope everyone can do start. Okay, belum lagi lah. Saya belum assign web assign lagi. Maybe next class. After next class, saya akan assign web assign. Korang rehatlah dulu Buat siapkan apa yang patut dulu. Okay, bye guys. Take care. Have a great rest of the day. I will talk to you on Thursday. Bye-bye.
Thank you,
Thank you,
Doctor.
Doctor.
Thank you, 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 Doctor.
Bye-bye.
Thank you, Doctor.
Maaf salah silap. Okay, saya maafkan. Tak pernah simpan pun. So tomorrow punya class is bye Aizat. Tomorrow's class is k19. Oh, esok ada lagi. Okay, that's good.